Okay, hello everybody.
Hello.
Hello.
Can
Hi.
everybody hear me and everyone else okay?
Yeah.
Perfect. So let me just fix my screen sharing here. Thank you all for joining us, and thank you for the folks who are watching for joining us. I know that on the Pacific Coast especially, it's quite early, so appreciate anybody who is here early so that our colleagues are able to join at a time that's best for them. So my name is Veronica Weiner. Welcome to the last industry event that we have at ProbProg. This is the second of two panels where we're discussing probabilistic programming in the field, where we're interested in applications that are being field tested or deployed arising from the research that we're performing. Yesterday we focused on Bayesian data modeling, and today the topic is complex simulators. So the focus of this session is probabilistic programming research in academia or in industrial labs that is relevant for potentially relevant for industry applications, and particularly those where we're using simulators to generate training data or using simulation engines in the loop at inference time. So to introduce the topic a little bit, the field has been very excited about simulation engines and the potential physics simulators that involve renders of visual scenes, and the opportunity to use those in connection with probabilistic programming, enabling applications that otherwise weren't possible, or creating the possibility of more human-like perception or reasoning. And in many cases, these simulators have been custom-built, or some of them have had substantial development outside of the field, be they physics simulation engines or otherwise, that we're creating good simulations is an academic discipline unto its own. And there's a sense that using these systems, sometimes developed over the years by very talented teams, has the potential to really empower us. So I will introduce each panelist very briefly, just a sentence or two. I will leave out much, and then I'll leave it to each of you to share more about your work. In the very next question, I'll ask each of you to speak more about your work, so we'll hand it over to you then. So the panelists here, you're all leaders and innovators in connection with using simulation in your work. Very honored for you to join us. You come from small and large organizations, industry and academia, and it's really great to be here with such esteemed folks, and I know that everybody is looking forward to hearing your perspectives. I am just moderating today, so very quick intro of myself, Director of Special Projects, MIT Probabilistic Computing Project, also managing partner of a small company with Vikash. I've done quite a bit of field testing and applications and working with PPL teams. So let me first introduce Nimar or Nim Arora, who is a research scientist at Facebook. We invited Nim yesterday and today because of his range of experiences and the time he's had working with applications and very inspiring work on global seismic monitoring for nuclear safety, using open universe probabilistic programs, and relevant to this session, geophysical simulation. Repeating a bit from yesterday, Nim likes to study why generative approaches work better than discriminative approaches, has built probabilistic programming models for Facebook and the United Nations, awarded prizes for Bayesian analysis, and to repeat a quote from a colleague that I said yesterday, his work is one of the most unambiguously morally positive applications of probabilistic AI that I've seen. So switching to Ashish Kapoor, also somebody whose work has really great humanitarian purpose with a focus on safety. Ashish is partner research manager for the Aerial Informatics and Robotics, or AIR group, at Microsoft. He leads a very large scope of research there, is an expert in machine learning and simulation software, especially in the AirSim platform, which builds with an aim to build intelligent, autonomous flying agents, everything from flying robots, micro UAVs, commercial jetliners, and this work is using techniques from probabilistic programming, of course, other areas of machine intelligence, robotics, human-centered computations. Some of the applications there are in weather sensing and precision architecture, and some that I thought were really wonderful were helping first responders perceive room layouts in smoky and dusty conditions certainly has great humanitarian purpose. And I had read about a wonderful application detecting animal poachers by way of virtual flying drones over the savannah. So an application where simulation really was an important part of the solution. So next I'll introduce Tejas Kulkarni, who is CTO of a relatively new startup, Common Sense Machines, whose purpose is to translate the real world into a 3D simulation, which is very exciting. Tejas is somebody who is an innovator, as many of us know, in Bayesian inverse graphics, and new work on real to sim and sim to real. Before that was at DeepMind as a senior research scientist for 3 or 4 years and did a PhD at MIT. And I know many of us were inspired and motivated by Tejas's earlier work with the picture language, which I and many others found to be a really compelling and memorable way to demonstrate to this field that inverse graphics is possible, efficiently achieved with very concise code in a probabilistic programming system. And today's work integrates deep learning, reinforcement learning, probabilistic programming to realize some of the promise of inverse graphics. And Tejas also represents somebody from a startup company, so that's an additional perspective for us. And last but not least, Gunesh Vaden is representing somebody in academic research who consults very much with industry as well, who is at Oxford in the a departmental lecturer in the Department of Computer Science, senior researcher in machine learning and engineering science. Gunesh has done very innovative work in physics simulators, working with large-scale European projects like the Etolumis, not sure if I'm pronouncing it correctly, project, collaboration with Intel, and does really great work on amortized and Monte Carlo inference for large-scale simulators. His work enables probabilistic inference in these large-scale simulators in particle physics. And so there's a focus on distributed training, inference at a supercomputing scale, and interfacing with high-performance computing, which I think is particularly exciting in thinking about the simulation applications. So before that, Gunesh had worked on automatic differentiation and some other work, hyperparameter optimization, evolutionary algorithms. So with those intros, we will now move on to the panelist questions. And I'll start with letting each person introduce some more about what they're working on today. So the first question that I have is, and before we start, we will take audience questions also. So if you have questions, please write them in the Q&A panel, Q&A tab. And those who are not writing, please vote on them. And we will take the highly voted on questions later on in the panel. So to start with, what simulators have you been working with? And are they designed for training, testing, or as models in the loop? And let's start with Tejas.
Yeah, really glad to be on this panel. Thank you so much. Very nice to meet everyone. I think I've basically played with a range of simulators. During my MIT days, played a lot with Blender and learned parameterized renderers. During my DeepMind days, worked basically used a lot of Unity. So we used to have large-scale Unity environments. So there, I think a lot of the use cases there that I saw gaining traction were using the simulators for training. And if you were basically in the robotics line, then using some of the physics simulators for behavior planning. But a majority of the use cases during my DeepMind days were using the simulator as a training ground. More recently, in the CSM context, been using a lot of Blender and CAD rendering tools as well. So now I think moving more towards the potential of using these simulators in the loop, not just for training. So I think the two biggest kind of simulators that I found useful are one is for asset creation, like simulators where assets are created, so things like Blender, Maya, those type, or CAD engines. And second is where environments are created, so things like Unity or Mujoko if you have physics. So those things have been very useful, both for training. There are three use cases really, right? The first use case, which is obvious in the field now, is if you have a really good simulator, then it's useful for training. or increasingly so for synthetic data. So you can actually use these simulators, and they're photorealistic. Like computer graphics is not as photorealistic before. So, and I think so. Synthetic data is a huge use case. I would say right now it's ready to be deployed. I think many startups are deploying it. It has found its use case. I think the more kind of frontier things for sensory motor knowledge is using the simulator in the loop. People are using that in academic context, but it's not yet there for deployment yet. But that might change in the future.
Great, thank you. Ashish, is that a similar experience to what you're having to create assets and environments? And could you speak about the simulators and use cases you're looking at and training, testing models in the loop?
Yeah, definitely. We started on the simulation journey back in 2014, 2015, when we were starting the robotics research within Microsoft Research. And if you've been to Seattle, out of 12 months, 9 months we have, weather. And, the reason we went onto a simulation journey was for our own utilization. So we created this simulator called AirSim that was focused mostly on aerial robotics at that time, and slowly the scope increased. The whole simulation purpose, I was built upon Unreal Engine as a rendering, front end, but at the back end, you had to simulate every sensor model, all the physics, all the propellers from the ground up, and to create something that would mimic an AI pipeline. So it was really an AI simulator, a machine learning simulator, so that, you can build your robots very rapidly without us going in the wet weather out. One of the things that I've realized, like I agree with you, is that probably the biggest impetus right now is machine learning training. So using simulation to generate data, and mostly supervised learning as well. There are a dime a dozen startups right now. They're trying to do, generate synthetic data and learn machine learning small for that. But I think this is just very one small vertical. I think we need to take a little bit holistic viewpoint on this, in the sense that, sure, it can generate training data for supervised learning, but also, reasoning in the loop. Also our ability to sort of do reasoning, which right now most of your machine learning is statistical reasoning, but it is a very nice tool where your logic and statistics can come together. So for instance, you have physics-based prior and things like those. And sure, some of this work is in academia, but I think in industry it's still long ways for industry to go. So one of the things that we are actually looking at is, if you go this traditional simulation route, which is something like Unreal or Unity or any other rendering engine, that off-the-shelf physics engine or physics engine that you create, or sensor models, the thing is, the time to deploy from a concept is quite big, and you need a large software expertise. I mean, you need teams who someone would excel in physics engine, someone would excel in rendering, someone would excel in just communication. So one of the things that we've been looking at is how you can make the whole pipeline completely neural-based or completely statistical. So from physics engine all the way to rendering, all the way to sensor modeling, all the way to communication, it's basically same computational fabric. And maybe it's a neural network. That's what we are betting on. Maybe we are a little bit wrong about it, but who knows? But the ability to create simulations rapidly. Right now, I think it takes around 3 to 6 months for us to incorporate a newer robot with newer form of sensors and things like those. I want to reduce it to a day. And that requires a little bit deeper thinking in terms of computational constructs that are fundamental building block of simulations.
Thanks, Ashish. Gunesh, I imagine that you have experience with these simulations that take months to build as well. I wonder if you could speak about the engines that you're looking at and what you may have been doing.
So I've been trying to categorize the simulators I'm working with into 3 categories basically. So the first one that you mentioned very well was the particle physics case. We used the simulator there that took decades to develop. It was like a C++ simulator the physicists were using to analyze basically, it's the essential piece in their data analysis pipeline at CERN. This is basically how they how they discover particles. They run these very large scale, very accurate simulators, but they don't do any Bayesian inference. They just use these things with hand-tuned like parameters to check like the likelihood of the data under one model versus the other, and things are completely hand-tuned. There is no automated inference or any notion of inference with these simulators. So this was one type. This type of one is very common with like collaborations with the scientists. The other type, so I've been starting to work on this year, is satellite orbit simulation. So I have a collaboration with the European Space Agency. There they have some orbit simulators. These are called orbit propagators. Basically, they are like simulating the trajectories of satellites in orbit into the future. They just care about like computing projections into future to find conjunctions, which are basically potential collision events. So they are trying to prevent collisions by simulating things into the future based on the current best knowledge about like where these things are in orbit. This is like a very, very important thing because currently people are launching like hundreds and thousands of satellites into orbit if you are following SpaceX and stuff. So this is going to be a huge problem, and the simulators are essential here. And nobody looked at using these simulators for inference tasks. So as far as I'm aware, we are doing that for the first time. So this type of simulator is not so complicated. The simulators are super fast in that space. That's very interesting. Like the physics simulator was extremely slow, but these orbit propagators are really, really fast. The third type is, I think, the one the machine learning people are more familiar with is like autonomous driving and stuff like that. You just run that. You collect large amounts of synthetic training data to use in deep learning. Again, you discard the simulator. You don't do anything useful with that beyond sampling training data for deep learning. Or in my experience, I've seen this type of cases. Yeah.
Yeah, so it sounds like also you types of focus in the loop and then creating some synthetic data for deep learning. And I'm very glad that you are paying attention to this satellites concern that so many of us have with all of the new satellites that Elon is launching. Nim, would you tell us about the geophysical simulators that you had been working with and who developed them and how long they took and the process of deploying? Because you have a deployment for a very important purpose in the Comprehensive Nuclear Test Ban Treaty that uses these simulators.
Well, yes. Well, first of all, I should point out that it sounds very fancy, but at the end of the day, it was actually a very simple simulator. But the reason I think we began looking at simulators is that we wanted to build a generative model. It was very hard when we were working with seismologists to agree on terminology in generative modeling. So we said, okay, let's step back. Let's say we were trying to build a simulator, and then they understood what we were talking about. And so we said, okay, let us explain to me all the physics that's involved if you were to build a very accurate simulator for your data. Because that's really what a generative model is at the end of the day. And so we were able to make a lot of progress with the seismologists, get a model of how events are generated in the Earth, how they propagate through the Earth, what they don't know, what they do and they do not know about travel times, amplitude decays, end detection. And so we built this model. Now our purpose was, of course, to make an open universe model with this and then use that to do inference. And this was a very funny part because, we built this model and we said, yeah, we understand every single part of this model. But what are you going to do with this again? He said, well, we're just going to put this in a PPL and we're just going to click infer on it. And we will get inference out of it. And that was the part that totally puzzled a lot of seismologists because they were used to doing things like inversions. And they were never, the idea of taking a forward model and using that to do automatic inference was quite new to them. And it was pretty exciting journey with them. So the initial model took me like about 6 months to build. The results were terrible. So they were like really beyond terrible, but we were lucky that they said, okay, fine, we'll keep funding your research and we'll keep talking to you and adding more. So then over time, I added things like, okay, refraction of seismic waves, reflection of waves, all kinds of phases of propagation. We did that. A year and a half later, we had better results than what they were getting. So again, the whole point was to build an accurate simulation so then we can do inference. So it took a year and a half to get better results. And then they started pointing out very interesting, subtle cases where we were going wrong. And then we would go back and say, oh, we don't have the physics on, Coda waves, for example. So we added that. we kept adding simulations which we could then show them. And this simulation data looks real, and then we would plug that back into our PPL and do inference and say, okay, then we've got better results. So it was very encouraging to see that having an accurate simulator of reality can then lead to very accurate inference. And so I would say it took about 3 years before we had a very accurate simulation. It's kind of stable at what we have right now. Yeah, it took another 10 years to convince people that using a generative modeling based inference approach was the right approach to do. But yeah, so that.
Very good. Yes, and I think that you've touched on some interesting questions about performance and optimization, and I think we'll get to those shortly. Before diving in, you've all described the simulation engines that you're using, and here we are at the ProbProg conference. So my next question is, how has probabilistic programming helped you the most? Can probabilistic programming, for example, in the style of Richie's work on procedural graphics and constrained scene generation, or the scenic probabilistic language from UC Berkeley, help generate more valuable simulation trajectories for training and testing simulators? Or you could answer generally, how can probabilistic programming best be integrated with your simulators to create value? So anybody who may like to reply to that?
Yeah, I can offer a few insights. So, some of the use cases we see in industry comes from the fact that there exists no simulator. I mean, there are some heavy industry folks who wants to use reinforcement learning, who wants to do some kind of causality inference. All they have is data. They don't have any simulation or a notion of a generative model or any statistical model. All you got is data traces, and I think the perfect thing there too is to fit a probabilistic program, or at least a model that kind of mimics the execution or the generation of that data. So it's a very important use case. I don't think a lot of people realize that there is more you can do than just fitting CNNs or simple neural network models to it. But one of the things that's very difficult to deal with is the notion of time granularity. Right, the statistical models do really well in terms of modeling the statistical correlations or at some point causations as well. But the time granularity, you might have multiple components evolving over time. It's actually a program, a real program, and dealing with time granularity is something that I struggle with all the time. Right, I might have 3 or 4 components. One is moving at 30 frames per second. Other is going at 5 frames per second. They need to talk to each other. There's a causal dependency. How do I deal with time? And that's something that I think is still an open problem and give us the most challenges. But that's a very natural place a probabilistic program have a very deep impact right away.
Yeah, maybe I can add something quick to that. So yeah. I think I should refer to the case where people don't have simulators. The other extreme is also possible. For example, in the science collaborations I'm a part of, they have simulators that they have invested so much time into. It's the perfect model. They have it sitting there, and they don't consider any inference or Bayesian anything with that. So that thing also happens. I'm more familiar with that case. It's good to keep in mind.
Yeah. In cases those simulators take long time to just generate a sample, so it's more efficient to fit a program to it and run it on a cloud.
That's interesting. Tejas, have you encountered the same kind of challenges that I would imagine that Ashish was describing to begin with? The elements that are producing data at different different.
Yeah, I think that's why I think I'm also really interested in how do you create simulators, because that is, once you have it, also using them, right? So both of these things are really useful. One thing that I wanted to say on top of that, which is, if you take neural networks, they're getting really good at let's say 3D content or 3D stuff. But it's actually, the quality is not good enough in the real world use cases. So probabilistic programming can actually create a big breakthrough there, in the sense that when people create these 3D worlds, they have a certain language in their head, right? If I'm a designer, I went through design school. I know basically what the design abstractions are, and I use them to essentially create these environments, right? And edit them, iterate on them. So I think this area is completely unexplored, where you essentially try to look at what the abstractions are for that workflow. And really, that's where probabilistic the programming in probabilistic programming can play a huge role there, right? Because the abstractions in neural networks are much more general, but they're weaker in the sense of convolutions or transformers, self-attention. Those are definitely the abstractions that are useful for processing sensory motor data, but they're not the abstractions that are used for designing the environments. So I think one huge potential for PPL is to make a big dent in there.
That's great. I see there's a question with many votes coming in on the Q&A panel. So let me ask that one, which may be timely. It's from Vikash. Nim, when using the simulator metaphor to design a generative model in the loop, how do you think about trade-offs between causal fidelity and feasibility of parameter estimation and inference?
That's a very great question. I think practically, ideally we want to know, be as accurate as possible. And sometimes if you build a very accurate causal model, it can make the model extremely difficult. So when we start out talking to these people, experts, like for example, if I were to sit with Tejas and build a PPL for the kind of notions that he just described, I would try to be as causally accurate as possible. And then, we would still sit back and look at the model that we ended up with and say, all right, well, does inference have any hope in this model? And then how can we, simplify this model? What kind of coarsening can we do into that model? But it's definitely an area where, a lot of automatic exploration of coarsening of complex models is worth exploring.
Yes, the coarsening idea, I think that can lead to another topic. We spent a moment on the promise and the the probabilistic programming constructs, and maybe we can talk about some of the limitations or obstacles in addition to the people would want to focus more on the promise as well. We can do that, but inference quality testing can be challenging. There's a sense of the value of looking at coarsened models rather than full-scale models as a strategy for inference that has to happen in a short period of time. I wonder if the panelists could discuss some of the challenges around inference quality, testing ahead of deployments, or other bottlenecks that they may be encountering. And maybe we could start with Ganesh or Ashish. I see that your microphone is off.
Yeah, definitely. So, this whole idea of inferring from after you learn from simulation, I think the sim to real problem, that's the umbrella I put a lot of this discussion in. Primarily, most of our experience is in the context of reinforcement learning and supervised learning. And one of the very popular ways of dealing with it is mix it with real world data. Basically, you're saying, you regularize with real world data, mix it, and you have some validation. And specifically when you're deploying in the industry for use cases, that's what you would do. But I think there is a principled way of going about things in the sense that, and I'm sure, there are hundreds of papers these days on thinking about sim to reality, which are very, very much domain specific. But in the end, I think it closely ties to the robustness of AI and ML models and inference models. And that's something that we have been thinking very, very, very actively about. So not just mixing the real world and the similar data, but from the get-go, can you design robust models? And the great thing about simulation is actually you can embed some of the robustness tests while you generate the data itself. So that's just our viewpoint. While we know what's the popular way to do things, but there I believe exists one abstraction which might be applicable across many use cases.
That's interesting for testing for robustness at simulation time for the various components. Seems like one way that you could do a lot of that in parallel to you have different components that are being simulated. Would other folks like to weigh in on limitations, challenges, bottlenecks for the probabilistic programming?
I think one broader point about robustness is, let's say a neural network works really well for your problem. And I think it works really well. You spend a lot of time. But then because all of the knowledge is stored in the weights, as opposed to in PPLs, you can actually do search and inference. So, and I think if you can transform the problem into a search problem after doing learning, then I think you have a better chance at generalization, right? So if you have a simulator, then you can actually do, you can do search and inference and improve your results. So where learning like drops you, and then, you know, where inference and search can like take you beyond the data, right? Beyond the interpolation, extrapolation of your neural network. So I think it plays I think PPL and just inference in general could play a big role in kind of giving you that generalization boost on top of your learn predictions.
Yeah. So if I may add, you know, the thing is, often in machine learning, we want to train models for optimum performance. But when you're deploying sometimes real world, optimum performance is fine. I mean, what you need is a good performance that's robust. And I think, you know, that's something as you know, in general in machine learning and AI, I think we are not paying much attention to. There is definitely a trade-off. And I think the notion of robustness have to be mathematically well-defined. If it's some loosey-goosey definition, I can't compute over it. Right now, the most popular definition of robustness is, you know, put up some pixels and your neural network goes crazy. But that's not enough. I think it needs to be connected to the real-world consequences. And we completely missing that bit. And I think this is very much in the realm of programming languages, where you should be able to define the invariants and constraints as they tie to the real world. And I very much think that's part of the probabilistic programming agenda as well. But I think very little attention is being given to that. In the end, optimality is great, but for real world deployment, it's not necessary. I think, you know, you can actually have suboptimal models, but as long as they work good enough, but safe and robust.
For the safety applications in particular, what you're describing sounds absolutely essential to tie adequate robustness to real world constraints for certain for cars or planes. Or
if I could add a technical point here, I think some of the questions that you're talking about, what makes some of the inference things difficult for PPLs. So one thing it's worth pointing out is that when you look at the design of most of our current PPLs, there are, you know, two kinds of random variables that they kind of advocate. One are those with a stochastic dependency, where you say, okay, this is drawn from a normal distribution, and others are those of deterministic dependency, where you're saying, okay, you have a whole bunch of random variables, you're doing some deterministic transformation on them. Now, when you have observations on deterministic dependency with random variables, then inference becomes really hard, because you don't even know where to start. And that's kind of, and the reason I mention this is because when we are working with simulators, those are the kind of random variables that we end up getting. And so the kind of inference techniques that you can use in that domain get highly limited. I mean, some of the early work where, you know, you had forward sampling based inference, and some work currently on ABC inference, those are the techniques that become a lot more relevant. So it's worth pointing out that, you know, there is a big hole in PPL inference research where we don't really handle these observations very well, and it ties in very closely to simulators. And that's kind of one of the reasons why, you know, simulators cannot directly be used as generative models, because of this one reason. So just as a technical point to keep in mind.
Yes. I know that you've done quite a bit of work on ideas close to that.
So, I mean, I wanted to provide maybe a perspective again from the science collaboration side of work. So I think the issues there are a bit different, because, for example, if you go to a field like particle physics, they have a model, they trust the model so much, they can bet their life on the model, they really know that this is the model of the universe, I mean, that's a very different setting. And again, if you are in a setting where like you are simulating orbits in space, that's also something very well known, like a figured out thing. So there is an advantage of like taking probabilistic programming to this type of fields. If, like I'm maybe talking to students here or like people with like an interest in finding new applications. So it's good to remember that there are fields where you don't have the sim to real gap so much, and you can like do interesting things and get results. So that's one thing that excites me personally. I care about results achieved in these fields using probabilistic programming. But in these fields, there is another type of problem where you need to convince people that what you have is useful, like they can really trust that. And like the argument we've been making is like if you trust your model, you can trust your results and something like that. But like there are different like people problems. Like you really need to, for example, Vikash has a question here about like simulation-based inference in particle physics. The community is slowly moving to like regular machine learning right now in particle physics. They are trying to convince themselves they can use machine learning in their regular pipelines. It's like the next step to convince them to move to probabilistic programming, like as a general deployed thing.
Great. So I will, thank you. I'll take one more question from the audience Q&A, and then we will switch to a slightly different topic. So this question is from Zena. Do panelists have thoughts on how to compose simulators at different levels of abstractions that make approximations in a principled way? And I think that somebody else had a similar question about navigating, and this was how AirSim navigates resolution and latency trade-offs, and which is related to the top question. So combining different levels of abstractness and resolution and making these sorts of trade-offs. Happy to hear your thoughts on that for folks who've worked on that.
I can describe our experience with AirSim. So AirSim is a pretty complex simulation where you are simulating multiple components. So these components being at the very highest level, rendering engine, of course. Second being the physics engine, and the third being the sensor simulations. So if you're thinking about reasoning, basically a brain or some kind of a neural network trying to guide your robot into it, you have to simulate all the way from the environment itself, then when seeing the environment through a sensor, pushing all of those things through a physics engine so that things evolve, and then taking an action, that action goes and talks to the actuator, and the actuator does its things, and the loop continues. So there are multiple components that are working, and the kind of simulations that are happening are also happening at different levels. So for instance, when you apply electric current to a motor, that's something that needs to be simulated because you have all the RC circuitry and things like those. And once the motor starts spinning, you have aerodynamic forces that needs to be simulated. And once you have forces and torques, you have to apply your Eilers Newtonian physics to see. So it's basically nothing, but it's a collection of large number of simulations that are talking to each other. Traditionally, when we started from a software engineering point of view, this was all in code. This is, all your sockets and all those things, because we understand the physical process that we did that. But this is a non-scalable way to do things. So quickly, as we're moving towards more neural modeling of all of these individual components, the way we are doing it through through mechanisms that how graphical models have talked in the past for last 20, 30 years, which is basically things like message passing, where you have these constructs where you can talk to each other, and it can be a different granularity. So that's our take on it. Still, a lot of work needs to be done, but I believe some of the work coming from last 2 decades in graphical model inference has a very big role to play there. So I'll just stop here.
Super interesting. Tejas, would you like to touch on that? As I
I think those are all really
addresses
useful
some of the
principles
same
as well
issues.
what Ashish mentioned. I think on top of that, I think one thing that came up was like something that you just know are true, and something that you know are data driven. So I think that also is a useful way to organize different simulator abstractions. So what I mean by that is like, let's say if you're trying to model physical environment with lots of objects and scenes, then there are different simulators at different levels of abstraction. So at the lowest level, you're looking at raw senses. So you might want to essentially integrate together all those senses, simulate how light bounces off, and so all the neural rendering techniques actually that's a neural simulator, right? It's basically simulating volumetric rendering. Then there are other models which basically sit on top of that, which are more like using rendering engines, both for generating training data, whether it's like meshes or images or whatnot. So That's one level on top of that, where you're essentially looking at, higher levels of abstraction. And then even one more level up on top of that is basically where, some of these environments, you're writing like a game engine, right? Or you're writing like you're constructing a scene as a designer. And that's another level of abstraction. So if you look at these 3 or 4 levels of abstractions that are there in the real world, I think we should directly pull those out and compose them and have inference and learning that, essentially uses them productively. And I think we are seeing a lot of benefits in doing that. And I think, if you break up the problem in that way, then I think then the inference problem becomes tractable. So there are things. So I mean, the point is that there are just things that sometimes we know through science. How to break up the levels of abstractions. Just like in particle physics, maybe we're not as sure about our theories of how light bounces off, or how to do sensor fusion or 3D, like we do in particle physics. But there are certain core truths, if you will, right, that can be used to break up the simulator for sure.
It's very interesting. Okay, so thank you. I will ask one very quick closing question, maybe just a couple of minutes, I think focused on Ganesh and Ashish, and then we will close with any calls to action or closing comments from each of the panelists. So this question is, how often do you think about hardware, and are there particular hardware innovations that are guiding your thinking about 2021 or even into the future? And I know that Ganesh spends a lot of time on high performance computing, and Ashish, you've mentioned quite a few hardware innovations that you think are important on the pipeline.
I think my quick answer is
so
it
maybe
depends
Ganesh,
on
to
what you're working with. In particle physics, things are super slow. Then we got support from like Intel developers to make like compilers behave better, for example. It helped us. For other fields, like it doesn't really matter like that. I mean, yeah, it depends on the simulator you are working with. That's the answer for me.
Yeah, I think that we've been working with Intel as well, thinking about some hardware opportunities in these types of simulators.
Yeah.
These types of systems. And Ashish?
Our thinking around here is guided by the fact that I want to create a real world system ASAP. So it's not just some of the impediments because of your inference or creating a simulation, but also in the real time. Once you have a model, I want to just flip a button and it just goes on the robot and go for it, right? And I think one thing that's very important for that is there needs to be a parity between simulation and how that your real world robot is going to work with. When we started AirSim work, the biggest bottleneck was rendering engine. So, of course, we were thinking GPUs like everyone, right? But one of the things that has shifted is as we are moving towards a simulation, which is all neural fabric or some fundamental, computing unit, that's what we are now optimizing for. Basically that unit needs to be, we should be able to run that either in simulation, in cloud, or on the edge, and that has to be, so again, that's the guiding principle. I don't have very specific answers on what hardware we are betting on, because I think this is still in the process. But that's how we are thinking about it. That flip a bit, everything runs on the real world, and whatever that will be enabled, we'll basically go with that.
So on the hardware front, if I could just add on the hardware front just a little bit.
Thank you so.
I think so. We have found some very interesting new developments. So I think there's this new chip called the IPU, Intelligent Processing Unit from GraphCore. And we have done some very interesting experiments on very large-scale simulations of the COVID disease model, I think, which we found to be very different in the sense that unlike GPUs that are more optimized for matrix computations, IPUs are more optimized for graph structured computations. And this is very relevant for us because when you're doing complex simulations, you have a lot of sparse structures. And that what we have seen is that the IPUs can give a 10x advantage over GPUs with equivalent number of compute units. So that is one hardware trend that we are watching very closely.
That's very interesting, and it sounds like this is one field within probabilistic programming where hardware is all of you are thinking about hardware without, of course, having taken a bet yet, and watching for developments. So We will close. Looks like we're close to the end of our session, or we're about a minute over. If anybody has any calls to action for the audience or any statements, I will just invite people as my call to action to join the poster session, which is next. Let's see, let's go alphabetically here. Nimar? Anybody would like to call to check out an open source project, to participate in any sort of event, take a look at something that you're working on? Otherwise, we can close and go to posters.
Yeah. Sure. Yeah. I mean, I think at CSM, we are really interested in simulators, and we're also really interested in probabilistic programming languages. And I think we're really excited about, what happened with AlexNet, right? Deep learning. So we want to recreate that. So talk to us if you're
Yes. We had a question about AlexNet that we have run out of time. How will we get to our AlexNet? So let's have that as a topic of discussion when people meet at the roundtables. I think that we're all thinking about the same thing. Ganesh, any closing calls to action or? Okay, very good. Ashish?
No, thank you for inviting us. This has been fun.
Thank you so much for joining us. Really insightful. I enjoyed that a lot, and I think that the audience probably did as well. So we'll see you at the posters now, which are on the first and second virtual floors.
Thanks.
Thanks, everyone.